Hello everyone, in this video I am going to prove bounded monotone convergence theorem, which says that if the sequence an is bounded and monotone, then it is a convergence sequence. For those people who don't remember what is monotone, monotone means that if your sequence is an increasing sequence or if your sequence is a decreasing sequence, you call that your sequence is a monotone sequence. In this video, I am going to prove this theorem for bounded and increasing sequences, and for the proof for bounded and decreasing sequences are similar. So let's assume that our sequence an is bounded and increasing. In here, boundedness implies that our infimum value and supremum value of this sequence exists. We are going to use only supremum of an. So let's call that supremum of an is a, and from boundedness we know that it exists. Now I want you to imagine what is bounded and increasing sequence. Think about one real line and consider our sequence an. Our first term a1 can be here, but a2 must be greater or equal than a1, and also a3 must be greater or equal than a2. And also we said that our sequence is bounded, and we said that supremum of an is a. So the maximum value of this sequence is a. Can you imagine one interval, epsilon interval? If a is here, a minus epsilon can be here, a plus epsilon can be here. And also you can see that a big N can be here, and similarly the sequence an is an increasing sequence, so a big N plus 1 it can be here. And for infinitely many terms of this sequence tends to a, it seems reasonable to say that our limit of this sequence is a. But how can we show that limit of an is a? Of course, we are going to use the definition of limit for sequences. What was that? For all epsilon which is greater than 0, we need to find one big N, right? Now we are going to use the definition of supremum, because we said that supremum of an is a, not a minus epsilon. That is why we have one term of this sequence which is greater than a minus epsilon. If you cannot find one term which is greater than a minus epsilon will be the supremum of an, but supremum of an is a. So because of the definition of supremum, there exists one n such that an must be greater than a minus epsilon for all terms of epsilon. And also for all n which is greater than capital N, we have what? As we said before, an is an increasing sequence. So if you say that n is greater than big N, an must be greater or equal than a big N, right? Let's use these two inequalities. In here, we said that an must be greater or equal than a big N, right? And also we know that a big N is greater than a minus epsilon. And also supremum of an is a. So all terms of this sequence must be less or equal than a. And again, we said that epsilon is greater than 0. So a plus epsilon must be greater than a, right? Now, just only think about these three terms, because if you think this is less than an and this is less than a plus epsilon, if you add minus a for all sides, we get minus epsilon, an minus a, and epsilon. This is the definition of absolute value, right? Absolute value of an minus a will be less than epsilon. Now you can see that for all epsilon which is greater than 0, there exists n such that for all n which is greater than big N, we have this inequality. This is the definition of limit. Limit an is a. So the proof is completed. For more real analysis videos, you can subscribe my channel. Thank you for watching it.